We live in a world where patients have the utmost faith in their healthcare providers, certain that they have the answers to diseases or illnesses that we might have little knowledge of. Sometimes, however, our healthcare providers are not so certain themselves. Take, for example, a pleural effusion. A pleural effusion is a buildup of fluid in the chest cavity that inhibits a person's ability to breathe. This can be caused by diseases ranging from severe pneumonias to stage 4 cancer. Effusion is drained using a catheter that is inserted into the pleural space. Nearly 200,000 of these procedures are performed in the US alone every year, with an additional 900,000 patients undergoing alternate chest draining procedures. However, in 26% of thoracentesis procedures, doctors are unable to determine the cause of the effusion. But why is this? Well, physicians today only sample 60 cc's of fluid, even though up to 1.5 liters can be drained from a patient. Some physicians believe that this small sample is not enough to accurately test for infection or malignancy. We are working to make this vision a reality. We introduce to you a brand new device to improve the sampling and collection of infectious agents and malignancies in patients undergoing chest drainage procedures. The new Pulmopivot device allows for whole sample filtration capabilities. This is possible through a multi-stage addition to traditional thoracentesis kits.
First component is a two-stage filter which separates and collects human and bacterial cells. When attached to chest drainage kits, this filter is able to sample the entire volume of fluid that is passed through to collection. The device works using a system of mixed cellulose ester membrane filters placed in series. The first filter has 12 micron pore sizes for the collection of human cells, and the second filter has 0.22 micron pore sizes for the collection of bacterial cells. After pleural fluid is withdrawn from the patient, it is pushed through our filtration device manually by a clinician using a syringe. Once filtered, the fluid will be stored in a waste collection bag for either protein analysis or disposal. Designed with luer lock fittings, the filter is compatible with most chest drainage kits and can be integrated right before collection. Up concentration of bacterial and human cells collected on the removable filter membranes will increase the likelihood of detecting pathogenic presence or malignancy from this procedure. We conducted both wet lab experimentation and mathematical modeling to validate our filter design specifications. In our wet lab experimentation, we tested the concentrations of E. coli before and after it was pushed through a 5 micron membrane filter. We found some E. coli remained trapped in the filter despite being smaller than the pore size. From this, we use a mathematical model derived from a stochastic model of membrane filtration to identify a new filter pore size. The model encompasses constriction, covering, and caking stages of filter pore plugging to derive a dimensionless conductivity equation, which we can use to determine flux and volume as a function of time. By comparing the computational mathematical models with our wet lab bacterial experiments, we concluded that the pore sizes of our two filters should be 12 microns and 0.22 microns. This past summer, our team has applied for a Duke MedX grant, filed a provisional patent through the Duke Licensing and Ventures Office, and drafted an IRB document which has been sent to Dr. Scott Schofer for review. We also initially reached out to local manufacturers to produce prototypes for our device, however have since transitioned to 3D printing prototypes in-house using Duke Bluesmith's Formlab stereolithography printers. Our goal is to begin initial design testing within the next few weeks for design optimization before moving to benchtop bacterial testing. Once this is completed, we will seek to obtain IRB approval to begin a clinical trial, which will be done in collaboration with Dr. Schofer, a pulmonologist at Duke Hospital. We are seeking design and potential user feedback so that we may further optimize our design. We are also looking for pulmonologists in addition to Dr. Scott Schofer to supplement our clinical testing.
To top it off, we already have in place a top-tier team. With 4 Duke biomedical engineers, 2 medical device professionals, and a practicing pulmonologist, our team has the expertise we need to make this device a commercial success. This has been Pulmopivot. Thank you.